Lead tin casting and scanning electron microscopy by Alex Braithnick, Sergio Brown, Kaylee Lamb, and Samantha Lanu.
We'll begin with an introduction to the scanning electron microscope. Scanning electron microscopy is a characterization technique primarily used to provide topographical and compositional analysis of a variety of samples including bulk solids, biological samples, thin films, polymers, and powders. Non-conducting samples are required to be coated with the conducting layer in order to avoid the occurrence of electron buildup on the sample's surface. Here, we'll discuss the components of an SEM and how those components work and interact with the sample. Let's start with the electron gun. SEMs use either a thermionic emission gun or a field emission gun. Since the SEM used in this investigation has a field emission gun, we will not detail the operation behind the thermionic emission gun. By applying an electric field to the tungsten crystal, a very bright beam of electrons is generated and emitted from the tip of the crystal through a tunneling effect. The electrons are then accelerated down the column towards the sample. The acceleration voltage depends on the potential difference between the cathode and the anode. Before reaching the sample, the electron beam travels through a series of electromagnetic lenses. These lenses assist in reducing the beam size, focusing the beam, and demagnifying the cross-section of the beam. The electron beam is then raster scanned across the selected area of the surface of the sample using two pair of electromagnetic deflection coils. The scanned electron beam interacts with the sample, exciting either secondary electrons, backscattered electrons, OJ electrons, or X-rays from the sample, which are then detected by the Everhart-Thornley detector, VSE detector, or EDS detector. The signals generated from the electrons are then processed into an image displayed for the user.
Electron-matter interactions. When the primary electron beam hits a sample, one of four things can happen. Secondary electrons are formed when the primary beam knocks out a core electron. This inelastic scattering provides a topographic contrast where steeper regions on the surface appear brighter due to more electrons escaping. The second possibility occurs when backscattered electrons are created by elastic scattering with the atomic core where heavier atoms will appear brighter and lighter atoms appear darker. The third possibility could be that Auger electrons are emitted, which is caused when the primary beam knocks out a core electron, leaving a vacancy which is filled by an electron from a higher energy level, resulting in the emittance of an X-ray. The fourth and last occurrence results when this X-ray has enough energy to eject an outer shell Auger electron. SEM specifications. The electron gun penetrating the sample to a depth of approximately 1 micrometer generates free electrons and accelerates these electrons to energies in the range of 1 to 40 keV. Most SEMs can generate an electron beam at the specimen surface with a spot size less than 10 nanometers in diameter while still carrying sufficient current to form an acceptable image. Resolution of an SEM is determined by the diameter of the electron beam or the probe size diameter, where I sub p is the probe current, beta is the brightness, and alpha sub f is the convergence angle of the probe. The brightness of the SEM depends on the acceleration voltage V0. The probe diameter can vary in the range of 1 nanometer to 1 micrometer. The probe current can range from picoamperes to microamperes, and the probe convergence can be anywhere from 10 to negative 4 to 10 to negative 2 radians. The magnification in SEM is determined by the size of the area where the electron beam is raster scanned. The scanning in a smaller area will give higher magnification, whereas scanning in a larger area will give a lower magnification. Areas ranging from approximately 1 centimeter to 5 microns in width can be imaged in a scanning mode using conventional SEM techniques, thus getting a magnification ranging from 20 times to approximately 30,000 times in spatial resolution of 50 to 100 nanometers.
Casting. Lead tin samples were melted into a furnace inside a ceramic crucible. There are two main reasons that lead and tin were used in this casting process. One, lead and tin mix very well together at any percent composition. 2. Lead-tin alloys have relatively low melting points when compared to other metals. By mixing lead and tin at the composition where the eutectic point is, the mixture can transition from liquid to solid. These properties make this alloy very useful as a solder, which is a fusible metal alloy used to create permanent bonds between two metal pieces. Samples were heated in the furnace to a temperature above the melting point. After a certain amount of time, when the sample was fully melted, metal tongs were used to take the crucible out of the furnace and pour it into the dog bone mold. 3 samples were cast into molds and were all cooled in various ways. One mold was quenched in room temperature, another was air-cooled, and the last was furnace-cooled. The different cooling rates affected the microstructure of the samples. This was because they gave the liquid metal different times to recrystallize, which affected the final grain size of the cooled samples. Standard dog bone shape is traditionally used for tensile testing. After cooling, the cast samples were removed from the molds. Initially, there were problems with air pockets and noticeable vacancies formed in the cast samples. This was because of improper pouring technique, where the sample was not taken from the oven and poured into the mold quick enough. For this reason, the cast samples were not the samples imaged in the SEM. Other lead-tin samples were used.
SEM samples. The SEM model used in this investigation was a Hitachi S4700 FE-SEM, which also has the capabilities of EDX compositional analysis. This image details some of the main components of the SEM: the electron beam column, the sample chamber load lock, which is used to prevent loss of vacuum during sample loading, the upper detector, and on the left-hand side we have the lower and EDX detector. Lastly, we have the nitrogen tank used in EDX to cool the detector. Samples image. The sample image in the SEM was a lead tin mounted onto a brass stub. The brass stub was then placed onto a cylindrical disc on the sample mount. The sample mount was then placed into the load lock and placed in the center using a rod. The video provided shows a sample being removed from the chamber through the load lock. Imaging. These are the images obtained from the SEM for the lead tin solder sample. The lower detector image shows topographical contrast as well as compositional contrast. This is due to the collection of backscattered electrons and secondary electrons that are collected from the surface and the surroundings. The upper detector image shows sharper edges at a higher resolution than the lower detector. The upper detector collects high-resolution secondary electrons. As seen in the image, one can tell that the lighter regions in the lower detector image are composed of lead, and the darker regions are composed of tin, because lead has a higher atomic weight. In both images, the solder can be observed to have a characteristic eutectic structure. This type of structure is typical for solders used in electronic applications. Summary. In summary, 3 samples of lead tin were casted in a dog bone metal cast and were either air-cooled, furnace-cooled, or quenched in room temperature water. Samples were then analyzed using scanning electron microscopy to get a closer look at samples' microstructures. The eutectic composition was found to be approximately 60-40 for lead tin.